Okay, Sally is here. We're all here. And it's time to get started. Concept Coach. I meant to tell you yesterday at lab time to do through the end of chapter, was it 20? But I forgot to say that, so I will stick with the one day behind. But do through what it says for Monday, for Monday's class. So the rest of 20 and the beginning of 21. Remembering that they changed the section numbers, so you're going to one less than the section that the schedule shows us going to. Everybody clear on that? No? So for Monday, go through what it shows on the schedule. What does it show on the schedule since you're looking at it?
It says 21.5 to 5 to 7.
21.5?
21.5 to 7.
Oh, wait. Today is not Friday. Today's when it should be the one for Friday. Yeah, I was like, no, it shouldn't be that far. So see, that's why I'm working with her, because I forget what day of the week it is. So it's
21.1 to 4.
So it's actually 21.1 to 3 because they've changed it. So go through that's all of 20, and then through 21.3 for Friday. On Concept Coach. Thank you for looking that up, Cassie. That makes it a lot cleaner and neater. So, everybody understand where we are in the Concept Coach stuff? Just a simple 2 questions. Number 1 is concept. How much time do you estimate Concept Coach is making you spend more than you would have spent without it?
Compared to reading quizzes or in general?
Compared to what you were doing last semester.
Yeah.
What was that? Okay, 20 minutes per day.
Per class day.
Per class day, yeah. More than you would have with reading quizzes. What about learning? Do you feel that it is helping you learn better?
Yes.
Okay.
I have to read all the other chapters around that chapter.
Actually, yeah. Okay, so because I want to know, how people are feeling about it, and of course, your learning is the most important thing to me, but your time is also important to me. I don't want you to be spending enormous amounts of time on my class. It's just one of many you have. Well, but you're going to have the homework one way or the other. I would be willing to talk about that, although it would affect the next year's class, not you so much. But don't worry about it. You really care about the others, don't you? Okay. We're going to talk about electrical safety here to begin. And we have in old homes fuses. In newer homes we have breakers. Now if you look at the picture of the fuse, pretty simple. You have, it looks like a little bent piece of wire. Of course it's not really bent. That bend is to tell you it's a fuse. But all it is a little filament of wire. And the thickness of that wire is carefully calibrated to make it so it will get hot enough to melt when you have a certain amount of current going through it. So those fuses are going to melt when you get a certain amount of current. That's to protect us so we don't use too much current. In newer houses, instead of this, they have a much more complicated looking device. Now, I'll be honest, when I look at this, I see the classic that's not how you spell spy. Spy versus Spy from Mad Magazine. That's what it looks like to me. Does probably some of you haven't spent enough time reading Mad Magazines in your youth. So this circuit breaker is a fairly complicated device. It looks extra complicated to me. Like this here is just a latch. This thing right here is just a latch. That seems like an extra complicated latch to me, but you have this system here where it's latched closed, so you make a contact right there. If you make a contact there, then the circuit breaker is connected and everything works. If you have a fault, then it pops open and you no longer have electricity going. How does it have a fault? It measures it by just how much current is going through. It uses a method we haven't learned yet. But it's still just a device that is going to pop open when you have too much current. So right here, we have a panel filled with those kinds of things. And each one of these is sensing how much current is going somewhere. So you can actually look here and you can say, okay, so this plug here is labeled, 1C3, and look over here, and it's, this one here is the one that's for that. So if Chad was to do something silly like take a piece of wire and put it in both sides, this thing here would click, and it would stop sending electricity to it so it doesn't melt the wire and whatnot. Now that reminds me, I know I already told Tori this, the absolute worst ever devotional I've ever heard was at Tori's alma mater. Right? Did you go to Redwood? Yeah. It was for a science day, and they had a pastor giving his little science worship thought. And he talked about when he was a kid, he took metal clothes hangers and would put one side in one of these outlets and the other side in the other outlet and watch it spark.
Which pastor was this?
I don't know. I was just... You're telling like second graders this. They're going to go home and say, hey, that sounded fun. Now, with that plug, and I was going to look it up before class and I forgot to, but you have something like this, and one of them, let's just pretend that it was this one, is hot. That means it has 170 volts to minus 170 volts going back and forth. We call it alternating current because it's going back and forth. And then this one here is neutral, and this one is ground. What's the difference in neutral and ground? They're just two separate paths to get to the earth. Yeah. They're both fundamentally ground. So now, when you put that in, with this pastor was sticking this in there, if he was lucky enough to stick one side into the neutral, put that one in first, and then stick the other side into the hot, he would have a wire that goes from ground to the hot, and he would not get shocked. It would just go, it'd all dump it to the ground. But if he put it in the other order, then he gets, as we like to say, the bejesus shocked out of him. And it's potentially damaging. Just how many people have been shocked by the power that comes out of the wall? Okay, a good number of us. And we're all alive and functioning. So it might seem that it's safe, but it's not perfectly safe. We had a family friend whose 2-year-old daughter bit onto the cable of the vacuum cleaner. And, yeah, her brain function stopped developing at that point. And so she became a 20-year-old, still in the stroller. It was very sad, just because she bit into the power cable. Right, so it's not perfectly safe. There are some dogs and cats that like to eat power cables. I had a renter whose pet did that, and then you have sparks on the floor, and it's not good. Okay, so it's not safe to play with that stuff. I may tell some stories and laugh about things like the bad wiring in our house when we lived at Riverside, California. Every time I went to open the freezer in the garage, I'd get shocked by the handle of the freezer. And it drove me crazy, because I'd always go out there barefoot and open it and get lemonade, make lemonade, right? And so about the time we're leaving, we're doing something in the attic and messing with things, and we noticed that the junction box for that power, they had the wires crossed, so they took the hot wire and connected it to here and here. And so the chassis was hot, and that's why I kept getting shocked. That's the one that's supposed to protect you. And they just wired it wrong. Don't trust bad electricians. Okay, so let's talk about safety and why we have these fuses and breakers. One reason we have them is to keep our homes from burning down. The wires in the wall, they have a small amount of resistance. But when you put a lot of current through, they will still dissipate. It takes a lot of energy to make it go through when you have a lot of current going through, the V equals IR relationship. And so they get hot when you have a lot of current going through. Hot enough that they can catch on fire. And so we limit our household circuits to 15 amps. If you're going to have a circuit with more current, you need a bigger wire that's going to have, if it's bigger, the area is bigger, what does that make the resistance? Yeah, we had the equation that said that the resistance was equal to the resistivity multiplied by the length divided by the area. So if you make it a bigger wire, it's going to have a lower resistance and thus it won't get as hot. And that's what you have to do to have higher currents. Okay, so that's one thing we want. Another thing is safety. We don't want somebody to get killed by electricity in our house, so we have things like circuit breakers to try to help remediate that. Now I titled this slide, this is from a picture in your textbook, How to Test if a Wire is Hot. Now I cannot imagine the situation where you have to make this test. Right? There's always got to be a better way. But if you have to, if there's just no way around this, like the house is burning down, here's this electrical wire, I don't know, I would just jump over it, right? But who knows? If you, in the first picture, the dude's holding on to like a wrench, and he touches the wire with the wrench. And of course, if the wire is not hot, and by hot we mean it has electricity in it, if the wire is not hot, no big deal. If the wire is hot, then the electricity is going to go through that wrench, through his body, out to his feet, and into the ground. Not good, right? Now, best case scenario, it makes him go, ah, and fall backward. And if he didn't die then, he's going to be okay. But then you have the second picture. What if instead of using the tool to touch this, and actually the way I was taught this, when I was in high school working at the dairy, they taught us this. You have to check. Check with the back of your hand, go like this. Don't go like this. Don't come down palm first. Because if you come down palm first, the first thing electricity does is it makes your muscles contract. Because our muscles run by electricity. We talked about the heart. And so if you come down like this, and it's hot, you go, and you grab onto it, and you don't let go. And if you don't let go, that means you're going to go, right? Which is not good. And so you should never, ever go like this. And of course, if you do it this way, it's the best case of all, because if it's hot, you just go, and you slap yourself in the face like what an idiot I am. Right? That's the best way to do it. Better, actually, I think, than using the metal tool, because you got that metal tool and you get shocked. You could throw that into poke your eye out. Right? I don't want to do. I really do think it's better not to use the metal tool, because you'll be throwing something if it's. So, but my advice is don't do this. I have to tell you, when I was in high school, one of our maintenance faculty or staff, he checked fuses. We had things that were like 400 volt circuits. 400 volts can be really deadly. And he would check the fuses by going like this. Yeah, wow. Here I am, I'm 14, I'm all, is that safe? Oh yeah, it just stings a little, you know. Well, here's the thing. The fuse should be just a wire. And so if the fuse is good, electricity goes through the wire, you put your hand on there, it doesn't do much. Right? You don't feel it. If the fuse is bad, he licked both fingers because your skin has a fairly big resistance. Inside the skin is very low resistance. He licked 2 fingers and he touched on top and bottom, so the electricity would go in one side and come out the other and not go through his body. So just his hand is getting buzzed. But of course, if you touch like this side and don't touch that side, you touch the hot side and not the other side, then it would go through your body. And that's when it would become dangerous. And so even though, in theory, You put it on both at the same time, you're safe. It's kind of goofy to make that kind of risk, isn't it? So another thing not to do, just don't test things to see if they're hot. Effects on the body. Now, this is a graph, once again, from our textbook that shows different frequencies of electricity are different safeties. What's the frequency that we have coming out of the box right here? 60 hertz. How would you typify 60 hertz on the safety levels there? Yeah, it's pretty close to as dangerous as you can get. Pretty close to as dangerous as you can get because you have your effects both where you feel it and where you can't let go. Your muscles are involuntarily contracted, are about the lowest current necessary for those to happen at 60 hertz. So 60 hertz is more dangerous than direct current like a battery produces. Now, when people talk about safety, you will hear plenty of people say, it's the current, not the voltage. And they're correct. But current and voltage are intimately related. You have a certain resistance going across your skin. Since electricity goes in the skin one place, comes out another place, you basically double that. And that essentially gives the resistance to your body. So it doesn't matter if it goes in this finger and comes out this finger, or if it goes in this finger, goes across my heart and comes out this finger. It's going to be the same resistance from my body. And that resistance is basically set by how moist my skin is. If my skin is nice and moist, I'm going to have a lower resistance. If it's dry, I'm going to have a higher resistance. Dry skin is safer. Gentlemen who pay no attention at all to your bodies, you're living safe. So the current that's going to flow through your body is going to be the voltage divided by the resistance. Most of what we deal with is this here. We say it's 120 volts. It's 120 volts AC, which means going plus and minus 170 volts. So let's think about this. If your body's resistance is about, let's say, 2 kiloohms, and you have 120 volts, what should the current be going through your body? Really don't need the calculator. 120 divided by 2 is 60. And volts divided by kiloohms is milliamps. So that's about 60 milliamps. 60 milliamps is just getting close to the region where it can cause a heart attack. Which means that this stuff isn't very safe to play with. Now I'm going to talk about the safety concerns. First, this red line, the threshold for sensation. If something has a really low current, you just can't feel it. So let's say you have a car battery. What's the voltage for a car battery? It's nominally 12 volts. Some are as high as 14.8. So let's say you have a car battery, 12 volts. For the same resistance of your skin, divide by 10, that's about 6 milliamps. 6 milliamps is down here pretty much close to the threshold for you to feel. I generally say the threshold for you to feel is about 10 milliamps. So that 6 milliamps is, you may or may not feel something if you just touch it. It's unlikely you will. Now, of course, if you wet your hands and you put your hands on the poles, what do you do when you wet your hands? You lowered your resistance. Lowering your resistance, what's that doing to the current?
Increasing it.
Increasing it, you might feel it. Let's say you're watching Rambo. When they're torching somebody with a car battery, what do? They cut them up, flay the skin, throw water on them, and that's going to give them a very low resistance if they go from a place where the skin's been cut to a place where the skin's been cut. And then you could get dangerous or painful and dangerous currents out of the car battery. So, don't... You're not going to torture anyone, right? You don't have to take off all the skis. You just have to... No. Okay, so we have this here. Basic levels, I say 10 milliamps is enough that you feel it. You feel the burn. Okay. I don't even support him. I just thought it was funny. Feel the buzz. You go up higher, and notice you get here somewhere in the ballpark of 20 milliamps you can't let go. Now, if you have that 20 milliamps going through your body, you can't let go. Is that safe? Oh, yeah, sure it's safe. Let us imagine that that's going across your chest. So all of your intercostal muscles tighten up. So you go, and then what happens? Your heart would still beat, but you can't breathe. And it turns out you go so long without breathing, and that's bad for your health. So if you're sitting there going, you're likely to die from suffocation if that's going across your intercostal muscles. So it becomes dangerous down there at the level where you have the involuntary contractions. Now if we go up, you get to somewhere in the ballpark of, let's say, 50 to 70 milliamps, and that's enough to start making the heart contract. And so that will throw you into cardiac, I don't know how to spell arrhythmia. Let's just say cardiac problems. I know how to spell that word. So you get about 50 to 70 milliamps across the heart. That's enough to cause the heart to start doing, as my EMT teacher said, just quivering like a bowl of jelly and not pushing any blood anywhere. Because you have electrical currents that are doing things like going around in loops and stuff like that. You get up to about 1 amp, you're likely to just stop the heart. Which is safer, throwing the heart into an arrhythmia or stopping the heart? Stopping the heart is safer. In fact, if somebody has a heart rhythm that's not compatible with life, terminology once again, we learned EMT class, like a ventricular fibrillation, you have no perfusion in that case. You still have electrical activity going on, the heart's doing this action, but it's not doing anything useful. They put the pads on you, and different defibrillators will either measure the energy they're going to put out, or the, what's the other thing they measure? Or the voltage, I think. But they release a bunch of energy, create a big current across the heart. What's the goal of that defibrillator? Yeah. The goal of the defibrillator is to stop the heart. They want to kill you. Because if they stop the heart, there's a reasonable chance that it will restart on its own. And if it restarts on its own, it might start in a rhythm that's compatible with life. So that defibrillation is essentially like taking your heart and hitting Control-Alt-Delete. Back in the day when Control-Alt-Delete had an immediate effect of making the computer reboot. Now you have to Control-Alt-Delete, brings up Task Mangler, and then you choose. So that's what they're doing when they're using the defibrillator. Now, of course, when you put those large currents across the heart, you're also going to burn some heart. So it's not good for you. You don't say, hey, let's try it for fun. There's a good chance my heart will start again. Because you will permanently damage your heart. And in fact, when they do how many people here are trained to use defibrillators? Okay, so we got a reasonable number here. You don't start at the highest energy setting on the defibrillator. You start at the lowest one, you shock, and if there's no change in the rhythm, then what do? Then you up it to, well, at least when I took it, there were only 3 settings, low, middle, and high. You put it in the middle setting and you do it again. No conversion, You put it on the high setting, you do it again. Nothing happens, you do CPR for a minute, and you restart the thing. And after you go through, was it three sets of 3, you say they're dead?
No, I said
No.
it's 4 hours.
You what?
I think you have to do it for an hour unless the physician declares it.
Yeah, you can't stop.
Yeah.
Well, yeah. What was that? Okay. Well, our protocol was 3 sets of 3, and then all you do is CPR. You say, there's nothing I can do for their heart. I'm going to sit here and pretend I'm helping them until somebody else that has the ability to say, he's dead, Jim, arrives. That was our protocol. The first person I gave CPR to, he was blue already. At least I knew there was nothing I could do to hurt him. Okay. One of only 2 patients I ever lost. The other one was a suicide. So 1 amp is actually a little bit safer than 70 milliamps because it will stop the heart and you have a better chance of survival. But you get too much current going through the body and you start burning tissue. So going to a family friend, changing sprinkler pipes, had a squirrel in the sprinkler pipe. And so he went like this to get the squirrel out. And the upper side of the sprinkler pipe hit a power line. Yeah. And he fell dead. And they said, I didn't see him after this, but they said you could see the burn marks in his hands where electricity burned into him. You could see the burn marks in his feet where the electricity went out into the soil. And if you were to section him, you would have seen burn marks going through his body from that current. Right? Very deadly. So be careful with electricity. You know, it's easy to get cavalier and careless, I especially am cavalier and careless with radioactive materials. But it's potentially deadly. You don't have to worry ever about a 9-volt battery. A car battery you don't have to worry about unless you're in the really crazy situation. But if you're dealing with something like the voltage coming out here, don't mess around with it. It's just too many bad things can happen. Okay. What was that?
Well, I was going to ask you about when we did the static electricity stuff, and they were talking about how you can store up to 25,000 volts in the body. How does that work with that? Because you're still going to have the same resistance.
Yes, but the actual amount of charge is small, so you actually won't get any current to speak of because there's so little charge to move.
So how does that play into that
Well,
relationship, though?
you're not going to work as an ohmic material there because you're going to have the current. Well, the current is going to be small because there's not much charge. Right? If you had 1 electron and it was at 2 billion volts, it wouldn't be dangerous to you because that's just 1 electron. And that's the situation. You don't have enough charge on you. Okay, did you answer, Chad?
What?
Did you answer?
Oh, no.
Yes, sir.
What about, and this might just be those extreme situations, but what about when you're struck by lightning?
When you're...
There's a ton of current, because I mean, you
Yeah.
watch TLC long enough and you'll see something about someone surviving it.
Like we talked about, Chad has survived, Aaron. Chad's his brother. I can't remember his last name, though. Kent, yeah. He survived. My brother's art teacher at CVA survived getting struck by lightning. It damaged, I think, her hearing and vision on one side. You really can't predict what it's going to damage and if it's going to kill you. Because obviously lightning can... There was a famous situation. It was a soccer match in some African country where lightning struck and killed all 11 players on one side and nobody on the other side. You know, everybody assumed that there was some kind of foul play involved. By the way, there you go. Thank you, Jerry. You know, you can't predict what's going to happen. Yeah.
Yeah, on the quiz online for reading, and you said that 10 milliamps?
Yeah.
Is that where you start to feel?
That's usually what I use. It varies with the frequency.
Okay, because in the quiz...
Because, you know, if you're at like 60 hertz, it goes all the way down to about 1 milliamp.
Okay, because the quiz said 1, and then I got it wrong. So just a second.
Yeah, it depends on the frequency. And so they're rough numbers. Okay, so we had this. We had 12 people who said C, 6 who said B, and 0 who said A. What's the relationship between equipotential lines and electric field lines? Okay. I will just go to the next slide to talk about them. We've already learned about these a little bit. This is the last slide that we will have on them. But the electric field lines are the lines of force. They show you the direction the force will be if you put a charge. If you put a positive charge, the force will be parallel to the electric field lines. So these green lines are the electric field lines. They're lines of force. The equipotential lines are lines of constant electric potential energy, or constant electric potential, therefore, if you have a charge that moves along them. So if I have an electron that moves along an equipotential line, its energy is going to stay the same. That means it's going to cost me nothing. I don't have to do any work to move them. But if it doesn't require any work to move them along those equipotential lines, then what can you tell me about the electric force along the equipotential lines? If there's no work when you move in that direction, what's the force in that direction? 0. So the lines of force, the electric field lines, have to be perpendicular to the equipotential lines, the lines of constant electric potential. And so if you know the electric field lines, you can always determine the equipotential lines and vice versa. Hence, they basically give you the same information. But one's a vector form and one's a scalar form. And the people in calculus class know how to go between them now. Okay, another question. An electron is placed between two vertical parallel plates held at minus 100 volts and minus 50 volts respectively. Very similar to a question we had on Monday. What will the electron do when released from rest? All right, a little bit of a spread. But the majority said accelerate toward the minus 50 volt plate. Is an electron attracted to minus 50 volts?
No.
Nope. Is it attracted to minus 100 volts?
No.
Nope. It's repelled by both. And going with what Tori said, minus 100 volts repels it more strongly. And so it goes to the minus 50. The charge will always try to go to its lowest potential energy state. And since potential energy is charge multiplied by electric potential, it's, for a negative charge, going to go to the highest available electric potential. So minus 50 volts is higher than minus 100 volts. It's going to go that direction. And that is the key to how an electron gun works. So here's a television tube, a classic television tube that you don't see very much anymore. It was a lot easier to teach this area of physics when everybody had this kind of TV. So what you have back here is an electron gun. The electron gun is the part inside there. Well, actually, it does say electron gun and have a span above it, I just noticed when I drew that. The electron gun first has the filament with current going through it. It's just like an incandescent light bulb. In fact, it gives off light, like an incandescent light bulb. But it also is pushing off some electrons. And then those electrons are going to be repelled by the negative charge of the cathode and attracted to the positive charge of the anode. And it doesn't matter if it's minus 100 volts and minus 50 volts, or minus 50 volts and plus 50 volts. Okay, there's different voltages, I guess. I should have gone minus 25 to plus 25. It's the difference that's going to be important for accelerating. Now, as the electron goes from, let's say, minus 100 volts to minus 50 volts, how much does its kinetic energy change? Okay, so if it goes from minus 100 volts wow, to minus 50 volts, it's gone through a voltage difference of 50 volts, right? Plus 50 volts because it was going up. So the change in potential energy is equal to Q delta V, which is minus 1 charge of an electron multiplied by 50 volts. So the potential energy went down 50, and what should I use for my units? Electron volts. No need to make life difficult. So if the potential energy goes down by 50 electron volts, what happened to the kinetic energy? Why did it go up by 50 electron volts? Because, well, I was going to energy is conserved. So the energy that leaves potential has to go into kinetic. And so change in kinetic energy equals minus change in potential energy is equal to 50 electron volts. Just so we're clear on terminology, some textbooks use K for kinetic energy. That's why I put delta K. Our textbook used in the first half kinetic energy and potential energy. But now when we're talking about electricity, it's using U for potential energy, right? They mean U is what we use in potential energy very often. So often it's delta K and delta U for change in kinetic and change in potential. So those symbols, in my mind, they kind of whirl around. U and PE mean the same thing in my mind. And so I might spit out the wrong one. I try not to. Okay, so we have the electron gun that's accelerating electrons. Then they go into those two plates. I have two plates, and I put a positive voltage on one side and negative voltage on the other. What's it going to do to the electron when it goes through? Pull it toward the positive side. It's going to have a constant acceleration while it's in there. The time that it's in there is going to depend on its speed. So you gave it a certain amount of energy coming out of that electron gun, which is going to determine how long it's in there. And given the constant acceleration while it's in there, you can determine what its speed in the horizontal direction is going to be because of that deflection plate. And so the deflection plate voltages are just regulated to deflect a certain speed. And then you have a vertical deflection plate. So a traditional television, what you do is you have a vertical deflection plate and a horizontal deflection plate. For the vertical deflection plate, you make it so it does a complete line, goes down, does the next line, goes down, does the next line. So the voltages for the vertical deflection plate go in steps like this until you get down to the bottom of the screen, and then it comes back up to the top and repeats. So you just have stepwise voltages so that it's going to be on the top row for, 1/1000th of a second, and then the second row for 1,000th of a second, and so on through all of the rows on the television. And then you have the horizontal deflection plate. The horizontal, it's going to sweep. It's going to go across like this, come back, and go like that again. So this one here, the time and the voltage, is going to be going like this. So that the time from here to here is the same as the time from here to here. So it sweeps across, does the whole screen in the time that it's on that one line. Now, of course, this is for traditional television. You're shooting electrons at the screen, and then that screen has phosphors that when the electron hits it, just like when we talked about the phosphors in the fluorescent bulbs, the electron hits it, it excites the phosphor, and it gives off a color of light. You actually use 3 different kinds of phosphors to make a color TV. One that gives off red, one that gives off green, and one that gives off blue, the 3 primary colors of light. And you have 3 different energies of electrons, so you have to have 3 of these electron guns, each one with a different energy, and those phosphors will only respond to the right energy of electrons, and that's how you get your color picture. It's a great application from 10 years ago. Okay, talking about capacitors. Capacitors are things that store energy in the form of separated charge, which is equivalent to saying they store energy in an electric field. Now, I've been talking, I think it was Sally that I was saying, electric field is really a calculational thing. The electric field is meaningless until you put a charge there for it to interact with. And that tells you what the force is going to be due to whatever made the electric field. But when we move into electromagnetic waves, we're going to treat electric fields more like they're real things. And this relationship with the capacitors, we will end up saying the energy is stored in an electric field, so we can talk about the energy being transmitted by an electromagnetic wave. So 2 ways of talking about the energy stored in a capacitor. Either energy stored in the form of electric fields or energy stored in a charge separation. Either one is a fine description. So what are capacitors? The simplest capacitor is just 2 parallel plates. And so I've shown there on the left a picture of a simple capacitor. For everything we do in this class, you just put the same charge on the 2 plates, one positive and one negative. That is, you start with 2 neutral plates and you move charge from one side to the other. That's how you charge the capacitor for this class. There are funky things you can do to trap charge, but we're not going to worry about that. Construction, the simplest capacitor construction would just be to take 2 pieces of metal, put some kind of insulator between them, and bring them down and make a sandwich. And here are what industrial capacitors look like. We'll use ones probably that look like this in lab, but these are all just different examples of what capacitors look like. So what's the point of a capacitor? Actually, I already said it. What does a capacitor do? It stores energy in the form of, either, say, charge separation or electric field. Because they're both correct. You see this separation of charge created the electric field. So that's why either one is equivalent. Now let's talk about these capacitors and why they're coming up in class. First, our analysis is only going to be true for the situation where you have a uniform electric field between the plates. And it turns out that's a good approximation for all capacitors. It turns out to be correct. But what we're doing here is going to assume a uniform electric field. As long as the electric field in here, the space in here, is very large compared to the separation, it's going to work out. Now, given that, we have already shown using Gauss's law that there is an electric field created when you put charge in the plates. And this here is actually talking just about what I said, it's a good approximation. You have electric field by Gauss's law when you have charge in the plates that is calculated as electric field is equal to the charge density. The previous slide had sigma as the charge density, the charge divided by the area of the plate, divided by epsilon 0. This is just a different font for epsilon. Sorry, it looks different. So the electric field between those plates is only dependent on the charge divided by area of the plates. Now I have a clicker question here, kind of like a did you pay attention to the words I said? How can you calculate the electric field outside of a flat conductor with a constant charge density? Okay, 2, 15, 1, 0. Now, we'll make the obvious designation. We have not talked about Ampere's law or the Biot-Savart law yet. And in fact, only the Physics 252 people will talk about the Biot-Savart law. So those 2 laws have to do with magnetism. Couldn't be those. So it has to be one of the top 2. And Coulomb's law is useful for finding the force or electric field for point charges. Using calculus, we can extend it to more. Gauss's law is what we use for this case. We did it before. We made the little Gaussian, called a Gaussian pillbox. So the correct answer was Gauss's law. That's the one that allows us to calculate the electric field between the parallel plates. From our work we've done previously, if we have a uniform electric field, the voltage difference is equal to the electric field strength times the distance parallel to that electric field. So if I have two plates like this with the electric field going like that, then the electric field strength is going to be equal to, multiplied by the separation of the plates will be equal to the voltage difference on the plates. So I'd have like 0 volts and A volts, the voltage difference, A minus 0. So this relationship comes just from the relationship between voltage and electric field. If I substitute in the equation for the electric field between two parallel plates, as shown a couple slides ago, that's the charge density over epsilon 0. Since charge density is charge divided by area, then the voltage difference must be the charge. Now when I say the charge, here's something that's real important. That charge is the charge on each plate. One will be positive Q, one will be negative Q. So when I say that Q, it's not the difference in charge between the two. It's the charge on one plate with the understanding one plate's positive Q, one plate's negative Q. So I'll put that on my picture as well. This one here would be plus Q. This one here would be minus Q. So the voltage difference is that charge times the separation of the plates divided by the area of the plate. So you have a plate, area, length times width, and the permittivity of free space. All of this just comes from things we've already learned. How is that important? Aren't you wondering? Right? I come up with some equation, you're like, well, I don't have any perspective to say why that's important. Well, here's why it's important. We define the capacitance as the ratio of the charge to the voltage difference. So the capacitance is just a ratio there. So using the delta V that I had on the previous page, I can now take this relationship. I always write this Q equals VC because then I can remember, like, there's the store QVC, right? I think there's a store QVC, yeah. And so I can just put in for the delta V, and now I have an equation that says Q equals CQD over A epsilon 0. And I can take this and solve it for the capacitance. I can get, notice the Q's cancel, and C is equal to area over separation times epsilon 0. And so that's the physical equation for the capacitance of a capacitor. A capacitor, a thing that stores energy in the form of charge separation. The capacitance is the number that tells us how charge and voltage relate. And it just has physical relationship that's very simple. What are the units of this? Who knows what the units of this are? Well, we could put in the units of area, meters squared, over distance, meters, times epsilon 0, which is coulombs squared per Newton meters squared. That should be right, but we never write that. Instead, we define that unit, coulomb squared per Newton meter, is a Faraday, named after Michael Faraday, or farad for short. So 1 farad is equal to 1 coulomb squared per Newton meter. And so we'll talk about capacitance in units of farads. Yes? Okay. What was that? We'll see. Actually, yes, there is. There's a question on this. In one kind of computer, I know. In one kind of computer keyboard, we use this to measure if the key has been depressed or not. You make a capacitor here, and you hold it at a constant 5 volts difference. And since Q is equal to delta VC, then if you change the capacitance, you'll change the charge. So here's some typical numbers. You have the area is, it's 6 centimeters on a side, so the area is equal to, or 6 millimeters, 6.0 millimeters squared. You hold it at 5 volts and you depress it from 4 millimeters to 1.2 millimeters. That means the D is changing from 4 millimeters to 1.2 millimeters. You change that D, you're changing the capacitance. And by changing the capacitance, you're changing the relationship between the charge and the voltage. So the charge is equal to that. And so as you change the distance, you change the charge. And it determines if the key is pressed by seeing when a spike of charge occurs, when it charged up or when it discharged. So you press it down, you got a smaller D, which means a higher Q. Charge goes in, it says, it was pressed. You let it up, you get a negative spike, not depressed. Actually, there may not be a clear question. If this is not a clear question, then we're done. Okay, yeah. There's a clicker question to finish this up, and then we will be done. When a capacitive computer key is depressed, what happens to the charge on the capacitor? Tucson answer, there we go. We had 14 people who answered correctly. The charge increases when you push it down because it was inversely proportional to the distance. You push it down, the distance gets smaller. Okay. Do the concept codes through 21.3 for class on Friday.